This video I'm going to talk about analyzing data. Specifically, I'm going to talk about mean, median, and mode. So when I have, this is considered to be, by the way, one variable statistics, or I only have, it's not a sort of graphing relationship where you have an x, y. You just have single numbers that you're working with. So the most common way, these are called measures of central tendency. I'll throw that in the corner over here. Central tendency, because you're saying something about where the middle of the number is, or what happens a lot, or that sort of thing. So all that's in play here. I'm getting lazy on my handwriting lately, so I'm trying to fix it. So anyway, mean, median, and mode. Those are the big ones that you usually deal with. There's also range, by the way. Range in the case of one variable statistic would just be how spread out the data is, the biggest minus the smallest, that sort of stuff. And with that said, it's probably a good idea that we organize the numbers numerically first. If we put them in numeric order, it makes a lot more sense. My suggestion is if you do it by hand, once you write a number down, mark it out. So I look and I see that 3 is the smallest number. And then there's another 3, so I'm going to put 3 again. And then there's 4. So that's out. Another 4. And another 4. Then I need to put 6, 7. And this is one of those areas where not getting sloppy is in your best interest. Because if you scribble it on paper and you lose stuff, that's when you start to get these wrong. So there's my numbers in like a nice numeric fashion. So when I'm dealing with mean, it's the only one that doesn't have like a little code word that tends to go with it. Median, you tend to code word middle. Mode, you might say most. Mean, average, really. Some people have gone really far and said, like, you know, your mean teacher averages your low test grades together, that sort of thing. I don't really get in on that party, but it is what it is. Anyway, so really what you're dealing with is the sum of the values. So add them all up. And then you want to just divide by how many there are, so the number of values. So you might say something like sum over how many. That tends to be the short version of that. So if I did 3 plus 3 plus 4 plus 4 plus 4 plus 6 plus 7 plus 8 plus 10 plus 11. And my suggestion is if you're typing it in this way in a calculator, you just make sure that you have everything the way that you want it. So go back through and look at them, and it's supposed to be a 10. Go back through and look at them and make sure everyone's there. You should probably count the numbers. I know there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them, which is helpful for the denominator anyway, because the number of values is 10. That works. So I could just go like into my calculator and make sure I have 10 numbers there and they're the right ones. So I end up with a total value in the numerator of, so I'm going to have to make a little space for myself. Messed that one up. Didn't give myself enough room. So anyway, I end up with a numerator value of 60 over 10. So my mean value is 6 right there. That's how that setup sort of works. Now the median number would be the middle. Oops, I meant to do that in blue. There we go. So the median number would just be the middle. So what I need to do is put them out, all the numbers. So write them here. You don't have to rewrite them. You can just use the original version if you don't have to be able to see them very well. And then I tend to start at the left side and mark it out with like a slash down into the left. And then I'll go the other direction for the second one, just so I know that where I am if I kind of lose my place. And then I'll go back to the original direction, then in. In this case, I have two middle numbers. So what I need to do, if you just have one, that's your median. If you break it down into an odd number, so say there's 9, well, there'll be 1 in the middle, and that's your median value. In this case, I have two of them, so I just need to find the middle number. I mean, it's 5, but you can add them up and divide by 2, and you get a median value of 5. That's how that works. And the mode is just the one that happens the most. So you sort of, if I were to do a little mini frequency chart, and you definitely don't have to do a frequency chart with this. I'm just doing it for my own benefit. So for 3, there's 2 of them. For 4, there's 3 of them. For 6, there's 1. All the rest just have 1. So the one that happens the most is 4. So my mode is 4. If I had another 3 in there, or 1 less 4, you can have multiple modes, or it could be what's called bimodal. Or you can have no mode at all. If all the numbers are different, you just say no mode. If it has 2 modes, you just say, you just name which modes they are. So 4 and 3, that sort of thing. That's the gist of how it all goes. In terms of the difference between the mean and the median, you'll see that the mean value is actually greater than the median value in this case. Well, if we look at the numbers, that sort of makes sense, because you lose a lot of capital in the median setup because the first 5 numbers are just the same 2 numbers, and they're very close together. They won't be, but the 11 and the 10, which are much bigger in the second set, will stretch that mean value out a little bit. So sometimes you have to tell which one is the better which one better analyzes the data. Median will always tell you the middle, but it doesn't necessarily. Like if I was going to get an idea of what kind of test scores my students made on a test or whatever, I would probably use the mean as my setup more than likely, because if I just use the median, I could have a ton at one end and it may give me a little bit of a skewed. I sort of would like to look at the information from the mean maybe, or maybe I wanted to. I had one kid made a really good grade. Basically, I would want it to be the median, be the mean, because if I have a couple kids who make really good grades versus the other ones, it doesn't make the other ones look so bad. So I want to feel good about how things have gone for that test. On the other hand, if I was going to do a reasonable analysis, my original explanation was a little bit weird, I realize now. If I want to do an actual analysis, median's probably the way I need to go, just because it'll analyze the spread a little bit better. If I have a bunch of really low scores and just a couple high ones that would bring it up, the median would tell me that, yeah, things didn't go too well on this test. The mode would have no benefit to me for the most part, unless I had a whole bunch of hundreds or something. But the mode probably wouldn't tell me much in terms of the data. There's other situations where the mode is a reasonably useful setup, but in that case the mode would not be that helpful to me. But anyway, look at the data in terms of how it's sort of skewed around, and you get a good idea of which one, mean, median, or mode, is the best for you to analyze central tendency. Welcome. In this video I'm going to be analyzing data, central tendency stuff, specifically mean, median, mode, using a TI-84 Plus. So I have my data set there, the 7, 4, 6, 8 thing, and I'm going to go in and just make it happen. Now when you have one set of data like this, you want to just punch it in as a list. In order to edit a list, you go to the Stat button. So go in, and then under the Edit menu, just click Enter for number 1. I've already typed it in, so it should be, you don't have to put it in order before you type it in. In fact, in the Edit menu that I was just on, it has Sort A, which is sort ascending, so the numbers go from smallest to greatest, or Sort D, which is sort descending, so it goes down. So you could deal with that later, but for right now, the biggest thing is once you type them in, and you'll just type the number in, hit Enter, it'll take you to the next one. Go down to the bottom one. The last time you hit Enter, it'll fall below the numbers. Click back up. Just to see this number right here. It says L1, which means list 1, and in parentheses it has 10, which means there's 10 values in list 1. So you count up your values, and there are 10 of them, so you know that you have the right number in there. You might want to, just be thorough to go back and check, whatever. Anyway, now that I've typed it in, I need to quit out of the edit menu, so I'm just going to hit second and quit to get back to the main screen. From here, I'm going to go and just do some math with the data that I've put in the list. So hit stat again. Sorry, I'm going to do specific things, so I need to hit second in list. If you're working with numbers in the list and you're not just doing some sort of generic regression or whatever, you'll need to hit second list. That's where you pick the list, and it's also where you do some of the operations and math using the list. So the math menu has mean, median, and it'll give you standard deviation, it'll give you a minimum value, a maximum value, all that's there. Not a huge big deal. So anyway, I want to know the mean. So I'm going to hit mean, and then I need to go pick the list that it comes from. So here's that list. And you get 6. If I want to know what the median value is, oops, second list, I need to go over to the median here. So I'll do second list again, and I'll choose list 1. And there it is. Now to find the mode, and I think I already found the median. Make sure. Yeah, I did. Okay. To find the mode, in older versions, or like the TI-73 Plus, which is the middle school version, there's actually a mode button that it'll do it for you. In the TI-84 Plus, they assume that you can count. So the best you can hope for is organizing your list and then just finding the one that happens the most. So what you're going to do is go in and go to second list, so you can fiddle with your lists again. You could do this from the edit menu too. So hit OPS says sort A, which means sort ascending. And then you'll want to go second list again and pick L1 and hit enter. It just is done. It doesn't give you the information. Now you can look at your list. So I just hit here and go to your edit, and you just count the one that happens the most, so in this case 4. But in some versions of calculators, there's actually a setup that will give you the mode, but in this case, just kind of find the one that happens the most, and that's it. So done. All right, in this video, I'm going to talk about analyzing data, specifically looking at quartiles, interquartile range, and box-and-whisker plots. So I'm going to take my data that I have here, the 7468 line, and I'm going to just analyze it using those setups. The first thing that I need to do is rewrite it in such a way that I have it in numerical order. So ascending, preferably, 3, it's kind of McDonald's colors now, 3, 4, 4, 4, 6, 7, 8, 10, and 11. Now, when I talk about interquartile range, or when anybody talks about interquartile range that knows any idea what they're talking about, we're talking about breaking it up into groups of 4, like a quintile would be 5. So I tend to think of it in terms of a dollar bill, and then the quarters that could go into it. So in a dream universe, I could draw good circles, but I'm not living there, so you just have to accept the fact that these quarters are awful looking. So anyway, 25 cents. That whole thing. So there's 4 quarters in a dollar, essentially, is where I'm headed with it. Now, there's a couple points of reference that we need to make when we work with these. The first, which is the minimum number. And I realize how awful that color is against this background. So the minimum number. So we'll say min. In our dollar, it would be wherever it is down here, kind of min. By the way, the dollar thing will pay off because it'll make it really easy for us to do the box and whisker plot here in just a minute. The next thing that we probably look for is the maximum number, of course, because why have a min if you don't have a max? Max would come right here in the old dollar analogy. Then we'd want the median. Median would come right here at the 50 cent point. So 50% of your data goes to one side and 50% of the data is above that number. And then we'll have Q1 and Q3. So basically we'll have Q1 will be here after the first quarter. So it's essentially the median of the lower level, or the lower two quarters. On the other end, you'll have Q3, which is the median of this set of data. So in my little setup here, I need to figure out what the median is. So the specific amount for the minimum, by the way, would be 3, because it's the smallest. The maximum would be 11. Now my median is what I'd look for next. These cancel. So I'm looking somewhere between 6 and 4. So to get my median value, I'll do 4 plus 6 divided by 2. So my median value will just be 5. So here's my median right here. To get Q1, I need to look just at this set of data right here. I need to find the median value there, which is right here. So the Q1 value, and by the way, if I had 2 in the middle there, I would do the average of those two. So say it had been 3 and 4 together, or 3.5 would be the median, or the Q1. But the Q1 here is 4, because it's the median value of that first set, the first 2 quarters. On the other side of it, if I'm dealing with this set, the top half, so to speak, I want to find the median there. It's the 8. So I would say that my Q3 value is 8. Now what I can do with this information, I should also talk about interquartile range. I'll get to that in a second. What I can do with this is make a Box-and-Whisker plot, which will give me some idea about how the data is skewed, whether it's one direction where most of the data falls at one end, or that sort of thing. As you can see, there's a considerable distance between Q3 and the maximum compared to the minimum in the Q1. So that'll shift what the graph looks like, which will tell us that the data sort of shifted in one direction. It might push us to pick the median as opposed to the mean as our central tendency of choice, that kind of thing. So the interquartile range, I'm going to call it the IQ range, which is really unfair. So the int Q range, I don't know. Interquartile range is right there. Anyway, interquartile range is Q3 minus Q1. So basically, this distance right here, I need to know how far they are apart. So the middle 2 quarters, so the middle 50 cents. So in this case, it would be 8 minus 4. So the interquartile range is 4. And all of this stuff is really sort of an assessment of range. The maximum minus the minimum will give you the range of the entire data set. The interquartile range will give you an idea of what's going on in the middle, so you can sort of see maybe one of those numbers is what's considered to be an outlier. An outlier is a number that's way out of the scheme of things. And if we look at the Box-and-Whisker plot, we may be able to see if there's really sort of an outlier here. So let's make a Box-and-Whisker plot. Box-and-Whisker plots, you want to start out with sort of a number line underneath, and it has 2 dots, one at the minimum, one at the maximum. So I'm going to make my little setup. I'm going to have 3 at the one end, and 11 at the right side. So I'm going to make little dots here. Those are eventually going to be my whiskers. Now I need to make my box. I'm going to make a box that sort of looks like this in some form. So the first line I'm going to make is at Q1. So right at 4 there, I'm going to go ahead and make a line right here. That's Q1. The next line I'm going to make is at the median, so right here. And then I'm going to make another line at Q3. And then I'm just going to make a box out of it. And now to finish it off, I need to connect my whiskers. So I'm going to draw a line here and draw a line here. So if you see the box and whisker plot, you can tell, they'll say, what's the minimum value? Well, you go to the dot on the left, and it's 3. If they want to know what the median is, you look for that little line in the middle of the box, and it's 5. But what it really tells us is how the data is skewed. You can see that the median value is way down here as opposed to the whisker that's way up here. We can't really tell necessarily if 11 is an outlier based on a box and whisker plot. So I guess I should write that word up in case people have never seen it. An outlier is basically a data point that's uncharacteristic of the set. But since 10 is here, and 11's probably okay as an outlier. But if I had like 25 in there, that would be significantly further away from the rest of the data set. So I could say, yeah, 25 is an outlier. So the term outlier makes the most sense here. It's just the one that's way outside the overall feel, the tendencies of the number set. So way outside the number set, essentially. One that's kind of the weirdo outlier set number. So anyway, quartiles, just find your minimum, maximum, find your median. Q1 would be the median of the first group, or the first half of data points. The Q3 would be the median of the second half of data points. And find the interquartile range. You want to subtract Q3 minus Q1, find out how far apart that middle is, which is, not insignificant here. And then finally, you want to have your maximum number, of course. Make your little box and whisker plot out of it. And based on the one that I have right here, I can see that most of the data is sort of shifted down to the 4 or 5 range, and all my data is sort of skewed to the lower end, whereas 11's keeping it propped up. But there's enough numbers at the top to spread it out, so at least the interquartile range shifts up to 8. So it tells me something about the data. In this video, I'm going to analyze, or talk about anyway, analyzing data, quartiles, interquartile range, and box and whisker plots with the TI-84 Plus. So in case you ever need to do that, I'm going to go ahead and just get into it. Really, we're working with a list here, so I'm going to turn it on. I need to clear out my list. If I can get it to do it. Okay, generally you want to do it individually, because if you go up to the top and delete it, it'll delete L1, which makes it all kind of get wonky after a while. So it's just in your best interest to delete them individually if possible. Anyway, once you do that, type them in. And I'll go back up and check. There should be 10, and there is, so I'm ready to work with it now. This is what I'm going to end up doing is a one variable statistic, so I can get a whole bunch of information from it. So if I go into the stat menu and click over to the calc, which is calculations, I'll go to one variable stats and hit enter to pick L1 as my list. I'm not going to pick a frequency list, and hit calculate. If I click down a little bit, this is a whole bunch of information. You can get standard deviation there. You can figure out kind of what the values of the sets are and that whole thing. So what I'm interested in is what's minimum, maximum, Q1, median, and Q3 are. So just click down a little bit. There's the minimum value of 3, Q1 value of 4, median of 5, Q3 of 8, and max of 11. Now, I want to make a box and whisker plot which could tell me all that information as well. So what we're going to do, I'm going to quit out first. You have to still type your list in, otherwise it won't work. I'm going to use a plot here. So hit second and y equals. And you're going to actually turn one of the plots on. By the way, once you turn a plot on, you have to turn it back off, or when you try to graph normally, your calculator will go out of its mind. It doesn't understand what you're trying to do. So I'm going to hit enter. I need to turn that plot on, and I need to go down to type. I'm going to pick the one in the middle here, the box and whisker plot. Choose that one. It's going to ask me which list do I want to use, and I want to use L1, of course, and the frequency is fine. The thing is, my calculator right now is set up to graph normally, so I probably have X values of negative 10 and 10 or something like that. But my numbers go from the number 3 all the way up to the number 11, which is above 10, obviously. So I need to adjust my window a little bit. So I'm going to go into the window here. Not going to do it that way. I'm going to hit enter to choose the frequency. Might help if I just kind of quit out of it really quickly. Yeah, sorry. So I'm going to quit out now that it's all set up and ready to roll ski. I'm going to go to the window, and I'm going to change it. I usually go like one below the smallest number, so 2, and my x maximum, I'm going to put one above, so 12. And now that that's all kind of where it needs to be, I'm going to hit graph, and it should make a nice box and whisker plot for me. The cool thing about it is if I hit the trace button, it'll start telling me where all the information is. So mine tells me that the median is 5. If I click to the left, it'll tell me Q1 is 4, the minimum X is 3, and then you can go over and get Q3 of 8 and maximum of 11. So all that information is there for you. You can make it pretty easily, so it might be a nice way to organize your information. In this video, I'm going to talk about analyzing data. Specifically, I'm going to talk about the term percentile. Where you'll see percentile most often is in things like standardized tests, the ACT, the SAT, that kind of stuff. Those tend to pop out things like your percentile is this. So maybe you're in the 75th percentile for your composite score on the ACT. What that means is the value of your score is at or above 75% of the values that other students have scored, or including yourself. So 75% of the scores earned by students on that test were as good or worse than yours. That's what you need to know. Now, on the left, I have this little set of numbers. It's okay that some of them are repeating. That happens. So these are ACT scores, just ones I've made up. In order to find the percentile, I need to take the number of terms and then multiply it by the percentage. It's pretty simple. So let's just do the 75th percentile. I want to know what I have to score to get in that 75th percentile, because maybe that means something for college. I don't know. But apparently they're only picking people from my school to go, because, and I have a very small school, by the way, because only 20 people took it. But, you know, adjust, I guess. So I want to know where the 75th percentile starts here. So there are 20 terms. And I just want to multiply that by 75%. Specifically, I want to multiply 20 by 0.75. And once I do that, I can find the value of that I would need to make to fall in the 75th percentile. So I do 20 times 0.75, and end up with 15. That does not mean a score of 15. It just means 15 terms into the data set. 15 terms in to the set. So right there, that's the 15th term in the set. So in order to fall into that 75th percentile, I need to have a value of 27. If I wanted to get way up there, like I wanted to just, you know, overachieve a lot, maybe I want to get in the 95th percentile. Well, in that case, I would take the same number and multiply by 95%, which of course would be 20 times 0.95. And I would find out that that would be the 19th term in the set. So right here. In order to be in the 95th percentile of this group, I need to score a 34. So there it is. That's all percentile means. It's not overly complicated, but occasionally you'll get a question about this, and this is the way to find it. In this video, I'm going to talk about using standard deviation information to describe data, like where a data point actually falls. So in my theoretical universe that I'm dealing with here, I'm going to say that I have a mean value of 18. And I know that my standard deviation is, let's say, 4, something like that. So in this, what I'm going to do is just make a little number line here. So 18 would be my mean. To do my standard deviation, I'll do plus 4 up here. So if I have my setup numbers, 19, 20, 21, 22. Here's my standard deviation away from where it happens to be. That'd be 1 standard deviation above. And then here, 23, 24, 25, 26. It's another standard deviation out. I might call it 2 standard deviation. On the other side of it, one standard deviation away. Two standard deviations away. So if I want to know specific information about a number, so say I want to know where 22 falls, or I want to know where 10 happens to fall. Well, 22 is 1 standard deviation above the mean. 10, however, is 2 standard deviations below the mean. So basically it just gives me a sort of a reference point to explain where information tends to fall. Usually, it does depend on the distribution a little bit. Most of the data will fall somewhere between between 2 standard deviations away if it's a value that you're actually going to use. So you can get sort of like the 10 is way away from the mean. So that may be something that I sort of question whether I really want to use it in my analysis of the situation. Whereas 22 being 1 standard deviation above the mean may be something that I would consider a pretty solid data point that's okay and safe to use if I'm doing a very specific type of research. It just sort of depends on where you want to go with the information. But a lot of times you will have standard deviation pop up as being a tool that you can use to analyze where a point falls in the data set. So there it is. In this video, I'm going to analyze data, talk about standard deviation and variance using the TI-84+. So we're dealing with, I've dealt with standard deviation and variance, I should say, in a different video. Basically, you find the mean of a set of numbers. You find out how far away each individual data point in the set is away from that mean. Then you want to square that difference so the negatives aren't canceled out by the positives, so everything's positive, basically. Then you add those squares together. Then you, once you have the added square differences away, you just divide by how many terms there are, and that'll give you your variance. And then to find the standard deviation, you want to sort of eliminate the effect of squaring it by taking a square root. So you square root the variance, and it'll give you the standard deviation. Now, a calculator will do this relatively quickly for you, specifically in this video, TI-84+. So let's bring it up and see how it works. Now, in order to do this, I need to make a list of my numbers. I'm going to go to the Stat menu to do that and Edit. There's a list already in here. Be careful. If you go up and click L1 and delete it, it'll often delete L1 completely. So when you go back and try to use L1 to do other statistical things or Box-and-Whisker plots, or anytime you have to use L1, you'll think that the first one you typed in is L1, and it kind of messes with you. So it's easier sometimes just to sort of click up and down the list a little bit and then just start deleting individual points. Unless you have a gigantic number, I would probably go that route. Anyway, type them all in. There's not that many in this set because I just kept the one I did when I did it by hand, or I did the long explanation. I didn't want that many of them. So click back up to make sure the L15 is, that number should be, it means list 1, there's 5 terms in it if you're in the last number. So that way it matches in case you have a big set that you have to deal with. Anyway, now that I have my list, I can hit second and quit and get out of it. I'm going to go into the setup menu again, so I hit Stat. I'm going to do one variable statistics. So when I do that, I want to tell it what list I'm picking from. I'm not going to pick a frequency list here, and I'm just going to hit Calculate. Now it'll tell me pretty much everything that I need to know. It tells me what my mean value is, so it tells me it's 8. So if I were to pop that out, I would say, well, here's my mean value right here. See if I can get it to do it. I'm going to bring it back up now. So in this case, right here is my mean value, so I could say my mean value here is 8. And then what I really want to look for is the sigma, because that's where standard deviation kind of lives. And it is 3.1, or 3.098, this whole thing. So I might say, just like I found before. But the nice thing is it gives you all the information in one little setup. Very convenient. It tells you the number of terms in the series, and if you need to do some sort of quartile analysis, it tells you all that information. So it's good. Go ahead and use how it goes. It also, in this case, sort of gives you the sum of the numbers. It'll tell you the sum of the numbers squared in case you need to know that. The whole thing, kind of the world is your oyster in a way, I guess. So, but standard deviation is what you're looking for here. Just pull the sigma term, and you're fine. In this video, I'm going to talk about the idea of frequency tables and histograms. Basically, a frequency table is when you, first off, you want to take a set of numbers, so you want to have data, and you want to break it into intervals, which are basically even-sized groups. Evenly sized groups. If I were to do say 1 through 12 or something, I may say how many numbers in that group fall between 1 and 3, and then 4 and 6, and then 7 and 9, and then maybe 10 and 12. So those would be my intervals. I'm breaking it into groups of equal size. In most cases they're even. Occasionally they're not, but that's how it works. Frequency is how often or how many times a number falls into that group. So the number of data points in each interval. So maybe I have 6 of them that fall between 1 and 3. I have 5 here, 4 here, and 2 here. And then a frequency table, it's just a way to visualize that information. So it groups them in intervals and then shows the value for each interval. So it's like it's a table that displays the intervals and the corresponding frequencies. Basically, this. If I put what each thing is, so frequency, and then I'm just going to do a generic title here. So generic. I don't know what 1 and 3 equal. I was just making it up in my head. So whatever it happens to be, I'll just leave it blank, actually. So the other section should tell you the frequency. So basically, this setup right here is a nice frequency table. A histogram is just a graphical representation of a frequency table. Now a histogram comes in 3 basic looks. The first would be uniform. And I'm just going to draw it, but when I get to the question part, I'll actually explain how to make it look. So the first one is when you have a uniform is when they basically are all the same height. They can be a little bit off, but for the most part, pretty much the same height all the way through the sections. That's my histogram and its uniform. So uniform, same. And we're talking about the height, specifically the frequencies, but whatever. The next type would be skewed. skewed histograms would be off to one side. Have a whole bunch of stuff up here. But as it goes, it tends to sort of move out. Even have a little buffer there, but still, for the most part, a lot of it's over here. And the last type would be symmetric. Symmetric sort of looks like a building or a normal distribution, if you know what that means. You tend to have one big part in the middle, and then the sides are pretty close, and then it just sort of goes down. So essentially you have a axis of symmetry. You can break it in half. I could fold one part over the other. It doesn't have to be exact. It just has to have the general idea that it is symmetric. So you're looking for sort of a line of symmetry. Or you can fold it over. So that's enough of that. Let's do some. So the first one says that the number of eagles observed along a certain river per day over a 2-week period is listed below. Make a frequency table that represents the data. So I'm going to look, and I see that the numbers go from about 1 to 18. A reasonable number of groups probably there would be, let's say, I don't know, 5 groups maybe, or we could do 6. So if I wanted to do 6, I'd do groups of 1 to 3, 4 to 6, 7 to 9, 10 to 12, 13 to 15, and 16 to 18. If you spread them out too much, you're not really going to get a good feel for it. So it's sort of, sometimes it's a little trial and error about how many things fall into it. So I need to find, oh, it goes from 0, I'm sorry. So 0 to 3. So, which spreads that one out, makes it a little bit uneven, but, you know, that's okay. So what I'm going to do is look to see how many fall in that group. So there's 1, 2, 3, 4 that fall in that group. 4 to 6, 1, 2. 7 to 9, 8, 9, 7, so there's 3 there. 10 to 12, I've got 1, 2 of those. 13 to 15, I've got 1, 2 of those. And 16 to 18, I've got 1. So that's my frequency table. It represents the data relatively well. If I wanted to combine groups together, like maybe I did 0 to 6, and then I did 7 to 12, and then 13 to 18. If that's the case, I would do 6 for this one, 5 for this one, and 3 for this one. Now, depending on what I'm trying to figure out, either one of those is a good frequency table. It just depends on what the overall outcome is supposed to be. The first one gives me much more detailed information in terms of, I can get very specific. I mean, you could go down to, I guess, 1 in each interval, but that would seem kind of silly. But I could see that the number of times an eagle has been observed, 0 to 3 is definitely the biggest one, whereas it doesn't seem as, between 0 and 6, like seeing an eagle 6 times is kind of a major difference between seeing it 6 times and 0 times, or whatever it happens to be. So I would probably use this one just because it gives me more information that's detailed. Whatever. The second one also makes it seem like the 16 to 18 group would pop up more often than it probably would. So that's that one. Number 2, the data show below shows the number of games won by a football team in each of the last 15 seasons. I need to make a histogram. So to make a histogram, you have to start out making a frequency table because they're, very closely related. One's just another version of the second. Actually, I might do the data below shows the average number of text messages a day. That would make more sense just because it gives me more room to work it. So I have, this is text per day. and then my frequency. And here I have it going up to 22, and my lowest group is 1, so somebody's only doing 1. So I might do groups of 5. So 0 to 4, 5 to 9, 10 to 14, 15 to 19, and then 20 to 24. That should get everything covered. Now I just count them. Make sure you mark them out so you can see what you're doing. 1 there is between 0 and 4, and that's it. Not a lot of low-level texters here. Between 5 and 9, I have 1, 2, 3, 4, 5. Between 10 and 14, 1, 2, 3, and that's it. You'll notice I'm trying to use different symbols each time. That way I can go back and assess how I got my answer, just in case I need to check. 15 to 19, 1, 2, 3. And the last one, 20 to 24, 1, 2, and that's it. It's also a good idea, by the way, to check to make sure you have the right number of frequencies in your table to determine that you've gotten them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 6, 7, 8, 9, 10, 11, 12, 13, 14. So that works. That's my frequency table. Now for a histogram, I'm just going to, on the bottom, put text messages. And over here, I'm going to put frequency. So on my y-axis. So maybe 1, 2, 3, 4, 5. Sorry for writing frequency so small. I'm kind of running out of room. Now, in my 0 to 4 group, I only have 1. So that's that. In my 5 to 9 group, I have 5. So there's mostly 5 to 9 would be the most common number of text messages sent in our little group that we've created. And then I'll do 10 to 14, and they're at 3. And then 15 to 19, they're at 3 as well. And then finally 20 to 24, it only has 2. So that's my histogram. Basically, you just set the boxes, and each one of them represents one section of the frequency table. It also gives me a nice visual. I can see that this one here really doesn't, like the 0 to 4 group is very small. It's easier to just have it there. And it sort of gives me the idea that it tends to sort of, skew out this way a little bit, more so than it hits a big high point at 5 to 9, but it skews higher than it does lower, which means it spreads out that way a little bit better. So that's frequency tables and histograms. I'm going to see if there's any more things I need to cover. I don't think so. Oh, no, we're going to look at types really quickly. So we talked about the 3 types, uniform, skewed versus symmetric. This one has a little bit... Sorry, I don't know why I rolled down so much. This one has a little bit of skew to it. As you can see, it sort of fades off to the right. So it goes this way. It's positively skewed a little bit. So that's that one. And for number 5, which is another type, this is a perfect example, or not a perfect example, but a very good example of a uniform histogram, just because this one's the uniform histogram. I'm sorry. This is a perfect example of a uniform histogram. I'm looking at another thing while I'm doing this. My apologies. I've been doing this a long time today. Anyway, the uniform amount, because it's the same. You wear a uniform, looks exactly the same as everybody else's, so that's no, it's uniform. This one is symmetric. My bad. See how it sort of fades down a little bit? Any sort of like dual-sided descent is sort of the way that you want to go to make sure that you have a symmetric representation of your histogram. So that's it. Frequency tables, histograms, not that big of a deal. I'm sure you'll do fine. In this video, I'm going to talk about the idea of sampling and surveys as a way to collect information to make decisions. The first thing that we need to talk about is the idea of population versus sample. A population represents all members of a set. So if you're going to do a population of people who live in the United States, you have to deal with every single American has to be involved in whatever you're doing to get the total population of people in the United States. Now, that's usually impossible to get everybody to do in your set unless your set is extremely small. You can't get the population. So instead, you want to go with a sample instead. A sample is part of that population. So if I was dealing with the idea of here's my population, a sample would just be part of it. That's how they get polling data and stuff when they ask about political opinions, like 75% of Democrats say this. Well, obviously they don't go and ask everybody who's a Democrat to say what they believe, or Republicans either. What they do is take a random number, or they pick a number of people and try to assess them. Maybe random. I say random because I assume they're doing things in the best interest of the study, but in many cases they're probably not. So they pick a group of them, maybe 50 or 25 or 100 or whatever, and then they garner information about the overall belief system based on that sample. That's what they're doing. So the real goal is to try to pick a sample that's representative of your population. If you don't, it becomes a problem. This process is called sampling. There's a few different ways that you can do it. Some of them are listed here. The first is a convenience sample. A convenience sample is easily accessible. So if I wanted to poll somebody who were I wanted to poll Democrats about something, I might poll only local Democrats because I know where the local Democratic office is. So it's easy for me, or the headquarters or whatever, it's easy for me to go down there and just ask people. Now that might not give a realistic view of how Democrats think, because I live in one area and Democrats here may be different than Democrats in other parts of the country, but it's an easily accessible sample, so I guess that's good enough, but not really. The next step would be looking at self-selected samples. Self-selected is a nice way of saying volunteer. I ask people who are interested to give information. That is not exactly the best way to get unbiased information in your set, just because you're getting people who are passionate about it. If you only ask people who to volunteer to do it, you're basically getting people who care a lot about it in one way or the other. So they have a true opinion. They're not people who won't be affected by it or whatever. A systematic sample is a little bit more realistic. It has less bias in it. In this case, you want to order the population, and then you want to pick people at random intervals. Like if there's an elementary school and they need to assess something about field day or whatever, it would be ridiculous for them to go and the teacher who's assigned the activity to do the survey just picks people from their class because it's convenient. You're only getting maybe he or she's a 5th grade teacher. You only get 5th grade kid information. That doesn't help you. A self-selected sample is, hey, who wants to fill out this survey about field day? Well, some people who may be really interested in field day just don't feel like it or don't like the survey or whatever, so they just don't do it. Or you have to go online and they're trying to do other stuff, whatever it happens to be. A systematic sample would probably split the school, which it already is, into classes, so you make sure that some people from every grade, and then you have an interval system to choose. Like maybe you go down the roster and you choose every 3rd person until you get 6 respondents, which means you could potentially get somebody. You get the 3rd person, you get the 6th person, the 9th person, but then if the class only has 15 in it or whatever, then it'll cycle back around, so there's a chance you'll get the people who you missed before. So that's a systematic sample. You've organized it, you've organized the population, and then you use an interval to pick people, or maybe randomly, like you have them pick 6 people or whatever it happens to be. The other type is random sample. And this is where all members of a population are equally as likely to be chosen. Now, countrywide sort of random sample is very unlikely. You're going to pick from certain things. I mean, you can't get everybody. But if we're in our school scenario, for instance, if you just put all the kids' names in, no matter what grade they're in, all in, and you pick 50 of them out, and you shake it up each time and whatever, it's a random sample. So it's possible to do it if the population is small enough and make it legitimate. So those are the sampling types. So convenience, it's just easy for the person who's doing it. So the person who's sampling, it's simple for them. Self-selected sample means that they volunteered. Systematic sample means you order the population in some way, and then you use random intervals to pick them. And then a random sample with everybody has the same amount of likelihood to be picked for the survey as anybody, or for your sample group as anybody else. From there, we're going to look at sampling bias for just a second to determine whether these situations introduce bias in the sampling process. Bias would be that certain groups of people will be chosen over others. In the first one, it says, a newspaper article about property taxes asked readers to call the newspaper to express their opinions. So in this case, what you're really dealing with, of course, is a self-selected sample. Not sample, sample. And this is a bias method because you basically get the passionate people due to the passionate nature of the respondents. Only people who care about it deeply are going to call in. It's like radio shows with call-ins. They usually have to have reasonably large groups of people listening to them because, like, for every 15 or 20 people or something, you may get one caller. So it's one of those things about it. This is a self-selected sample. Self-selected samples are generally biased. The next one says a reporter interviews people attending a local sporting event. Well, this is a convenience sample. And this is bias because there's a little bit more homogeneous feel to how it goes. You're basically going to get sports fans. One of the things in the local system that I'm working in is they want to put turf out on the field. Well, if you go to a football game and ask the people who go to the game, a lot of them will say that they really support the idea of having turf. But if you go, to the library or something, they may say, well, couldn't that money be spent on books or whatever it happens to be? So in that case, you're adding bias into the situation by picking like-minded individuals, people who'd spend Friday night at a sporting event or whatever. And the last one says a political polling company calls every 30th person in the phone book. So basically they take the entire phone book and they call the 30th person each time. This is a systematic sample because there's a system in place. Anytime it says every 30th person or whatever, it generally means that it's it's systematic. I'm sorry. Now, is there bias in it? Possibly. Depends on what they're asking. If they're asking about phone service, then it may be different because some people aren't listed in the phone book anyway. That's back years ago. It might have been different. Even then, you're basically getting a certain subset of people who are in the phone book. So if you pull the 30th, is it as biased as going to sports fans and asking them about turf? No. Obviously not. But there is a possible bias there. The newspaper article asking for self-selected, trying to create a self-selected sample. It's much more biased. But there is possible bias in the idea that you'd pick people out of a phone book because some people are unlisted and some people only have cell phones and they don't list themselves in a phone book, that kind of thing. So depending on the phone book, depending on the question, there is a possible bias in place. So that's the kind of stuff that you have to consider when you sample a group. And the last section that I want to talk about is the idea of completing a study. What types of studies are there? And the three I'm going to talk about are observational studies, controlled experiments, and surveys. Now, observational studies are studies where the study is done in a way that does not affect the sample group. So an observational study is just kind of where you watch what was going to happen anyway. You're not affecting it, you're not changing anything, you're just sort of observing what's going on in the regular scenario that's there. The next type would be a controlled experiment. In this group you have two groups. You have the control group, and the control group is the group that you just keep normal. It doesn't change or anything. On the other side of it, you have the experimental group. The experimental group is the one that you actually impose treatment. So you actually do something to them, whatever it happens to be. And the control group just stays the same. So they're the status quo group. The nice thing about the control experiment is that you have some idea that what you're doing has an effect outside of anything else. Like you can see that specific change affected the people in the control in the experimental group versus the control group. But it's not always the best way to do it, and there are certain things you can't do. There are certain rules about whether you're legally allowed to affect one group and not affect another, and it just sort of depends on the scenario. And the last one would be a survey. The survey is when you ask all members of a sample set some questions. So in the first case, you're just observing what they're doing. In the second, you're splitting them into two groups, applying a treatment to experimental group, and seeing if they're affected, if their lives change in some way compared to the control group, which is the status quo and doesn't change. It's like you were never even involved. And the last one is a survey where you basically just ask all the members of your sample set some questions. Now, you can add bias in the survey questions, but I'll have a different video on that in the future. So that's it, completing a study, sampling a set, and looking for bias in that sample set. In this video, we're going to talk about bias in survey questions. A survey, of course, is when you ask every single member of a sample set, so like your entire school, for instance, a set of questions. The problem is the questions that you ask them, specifically the way you ask them in the wording, could affect how they answer. So what you're trying to do is not introduce bias into the equation. Bias is when you make the decision go one way or the other, even if it's unintentional. It's kind of like you're pushing the agenda whether you mean to or not. The first thing that you don't want to do is combine two or more issues. So, for instance, if I was doing a little informal survey, or I was doing a formal survey, and I said, should school days be shorter and start earlier? Well, in some ways, I could get some support for this, because a lot of people want school days to be shorter. Students, mostly, and teachers, people who actually have to do it, wanted the days to be shorter. But the start earlier part doesn't really sell. Where I go to school, or where I work right now, school starts at 7:30 in the morning. So let's just say, for instance, I saw this question and I wasn't really sure what it meant. All of a sudden, that kind of ambiguity makes the bias start to be eke into the equation, let's just say. Maybe that means that school days will start at 6:30 in the morning and they'll be 15 minutes shorter. So instead of getting out at 2:30 like the school does now, it gets out at 1:15 because we go an hour earlier, which would normally, the normal length of the school day would make us leave at 1:30, but we get out at 1:15. So 15 minutes less of school and only have to get here an hour earlier. That would be perfect for somebody who really likes afternoon, but not anybody else. So once I entered two components into the equation, it added bias to it, so it's not a good survey question. From there, we may deal with using double negatives. Do you not disagree? That kind of thing. Anytime you use double negatives, you're starting to add sort of murkiness into the question process, and people may choose the wrong thing in something that they don't mean. Overlapping answer choices. Overlapping answer choices are much like combining two or more issues in your question. If you give them choices and all of a sudden two things are involved in your answer, and it's sort of like, well, I'm answering this but not this, and that whole thing, that's when the overlapping answer choices become a problem. You want to keep answer choices as separate as you possibly can. I mean, they can have certain components that are the same, but you don't want to have them seem like, well, like the earlier start time question before. I didn't want one of the choices to be like start earlier and be 15 minutes shorter, and then you have start earlier and be shorter. It's sort of confusing about what does that mean. They're almost the same thing. So you want to make sure that they're as separate as possible. Using loaded words is a big deal. It's really how a lot of people who do surveys gain the information that they want to get even before they start. Things like, for instance, in the abortion debate, if you use pro-choice or you use pro-life, those are both positive words depending on what side of the argument that you're on. If you use the word poison as opposed to pesticide, that should be a problem. Anytime you start using adjectives, generally it becomes a problem. If you call a book, would you rather watch an exciting movie or read a boring book? Once you add those loaded words into the equation, you're pushing the mindset already. So you don't want to do that. And then asking a leading question. You don't want to ask questions where you say sort of like, don't you agree with this? Or wouldn't you say that this is true? Or blah, blah, blah. Once you start already assuming that they agree with you, then the questions become, kind of a big problem. The thing you don't want to do is have don't you agree that teachers are underpaid, or don't you agree that teachers get paid too much, whatever it happens to be. Once you start pushing that agenda into the equation, it becomes a problem. So, long story short, in your question, you should only focus on one thing at a time. Your answer should be very specifically answering one thing at a time. You don't want to use double negatives. And you never use loaded words, so don't use anything that sort of show a bias in the question. Don't presuppose things, and which would be the last one. Ask leading questions. You don't want to ask questions that already sort of assume they agree with whatever you're saying, and then they have to disagree, because it sort of changes the mode. They're not giving a choice anymore. They're doing a yes/no based on your assumption that they believe something to be true. So that's it. In order to avoid bias in survey questions, avoid those 5 things, and then you should be making a reasonable survey question. In this video, I'm going to talk about looking at data in terms of it being considered quote-unquote normally distributed. Let's look, before I even get to that, let's look at the idea of what types of, maybe various types of distributions that you would see. Just the most generic ones, of course. So a normal distribution, most of the data, like here's the mean value. So most of it sort of flows around the mean in, a pretty even fashion, even though that doesn't look like the greatest job ever. So if I sort of erase this around. So most of the data tends to fall within the mean pretty close. The further you get away from the mean in terms of standard deviations away, the number of data points significantly fall. The other options that you could have, there's a bunch of them, but most likely, you could deal with a distribution that's sort of skewed positively, skewed negatively. And it's because the mean would seem to go here, but you've got these negatives that flow out, so that makes it a negatively skewed data set. Or of course, you could have the opposite of that, where you end up with sort of a skew to the positive. So this is positively skewed data, which means that there's a few points that are really positive that are sort of pulling up the overall set. Now, but what we're talking about is normal distribution. The thing about normal distribution is it's used in a variety of cases, one of them being IQ. We also tend to look at really any metrics a lot of metrics tend to fall there, height and weight and that whole thing. But what we want to look at here is just what percentages fall in. That's the nice thing about normal distribution. I can get an analysis of what percentages of the data fall into each one of these groups. Now at the bottom you'll see they use this term for this little symbol for the mean value, but I'm going to change it to this. That's the mean value in the middle. So most of the data tends to fall generally there. This would be 1 standard deviation, 2 standard deviations, and even 3 standard deviations below. On the other end, you'll have 1, 2, and 3 standard deviations above. Now, for each section, 1 standard deviation below and 1 standard deviation above the normal distribution. This is called the normal distribution curve. It'll be something like 34% of the data will fall in each one of these segments. So the percentage of data between 1 standard deviation of below to 1 standard deviation above is 68% or so of the data, which is a lot. So a lot of it falls 1 standard deviation away. By the way, for IQ, for instance, my mean value would be 100, of course. That's how this is set up, with a standard deviation of about 15. So if we were going to do an IQ analysis here, we'd say 100 is the IQ at this point. This is about 85. This is an IQ of 115. 2 up would be 130. And then 3 standard deviations above the mean, you're looking at something like 145. Each one of these, to school officials and other people who are in intellectual analysis and that sort of thing, each one of these numbers tends to stand for something of importance. In fact, we identify intellectual or cognitive disabilities at that 70 IQ and below tends to be 2. That's why they pick that number, because it's 2 standard deviations below. A lot of gifted programming starts somewhere around 120, so it's somewhere between 115 and 130, depending on the state. That's just where people tend to qualify for those sorts of things. Anyway, moving forward, let's look at how much is between, what percentage of the data falls between 85 and 70. Well, as you can see, like these sets, that's a lot of data that's going on. Whereas here, not as much, because the 70 is a lot less data than would fall in terms of a percentage than would fall between the at 85. So what we're looking at here is a number somewhere around 13.5% on each one of those sections. So if I was going to go back to my analysis of how much data falls where, if I wanted to know from 2 standard deviations below the mean to 2 standard deviations above the mean, in that case I want to add 13.5 plus 34 plus 34 plus 13.5, because all those sections are covered. It's easy to fall for the idea that you just add the 13.5s together, but that's you also have to consider that 34s are there. And this number ends up being something around 95%. So it's really common to see these figures sort of made known to people. So we could say that 2 standard deviations above or below the mean, you're looking at 95% of all the data. So in an IQ sense, that means that all IQ, or 95% of IQs fall somewhere 70 and above, all the way up to 130 and below. That's kind of where that number is. Now, the percentage of data that falls between 2 and 3 standard deviations is even significantly smaller than it is between 1 and 2. At that point, you're looking at something around 2. I'm going to try to get a different color so it's relatively obvious that where I'm going with it. So the difference here would be 2.35%. That's just between here and here. So 2.35% here as well. So to get the distance between 3 standard deviations below and 3 standard deviations above, you're looking at adding the 68 that we had before, the 13.5 twice would be 27, and then you want to add 2.35 plus 2.35, so .7% of all data falls within 3 standard deviations above or below the mean value in a normal distribution. So you can really start to get the idea of, how closely packed the data is in terms of what huge percentages it would be for 1 standard deviation out. If I were to sort of chart it, I guess, I would say this 2 and 3 So that's a lot. So what does it all mean? Really, the big issue is that you need to consider how much data is recognized up to a certain point. Like if I wanted to know what percentage falls below 3 standard deviations below the mean. So less than, so x values less than 3 standard deviations below. So what I need to do is take all of the data that's above that number and just subtract it. Well, I know that all the data that falls between here and here would be 99.7. So I'm going to take 100%, and I'm going to subtract 99.7%, and I'm going to end up with, 99.7, I need to hit the percent. I'm going to end up with 0.3. Now, that's the distance of all numbers that are outside 3 standard deviations. So I need to break it into 2 parts because I just want less than. So I divide by 2 and end up with 0.15. So something like 0.15% of all data falls below 3 standard deviations. And sometimes you have to do, I want to know how much is above 2 standard deviations below. So there's a couple ways I could do it. I could add, at this point, by the way, you're looking at 50% over here and 50% over here. So what might be advantageous to do, if I was looking for 2 below, would just be to take 50%, which would be all of this on the positive side, and then add 34%, and then 13.5%. So if I wanted to know how much data was above 2 standard deviations below the mean, all I would do is add 34 plus 50 plus 13.5 and find out that 97.5% of all data is there. So be careful about what the question asks you. If it's asking you about a subset that's less than something, you need to probably do, you might have to do division because they're broken up into groups represented in that way. If they want to know just a little bit more than half, remember that it's easier just to break it at the mean and do 50% above just to make the calculations a little bit easier. So that's normal distribution set up in a way that I hope is useful to you. It's probably a good idea to have some chart somewhere with the percentages because sometimes it's a little difficult to remember them all. And there's a little bit of the 68% thing. There's sometimes you'll see it at like the 67 range, but just adjust for your needs specifically.